All right, welcome back to Intro to Nanoscience Technology. I'd like now to turn to the atom, return back to the atom and the discussion of what Max Planck's and Einstein's and others' insights into what energy and what energy values can be taken inside an atom, what that means to the structure of the atom. All right, so let's consider a hydrogen atom, and I hope you remember from your prior courses that a hydrogen atom has a nucleus that is positively charged with one proton, and there will be an electron. And that electron will take a value in space because indeed electrons can be particle-like, right? So if we look for the electron somewhere around the atom, then we should be able to find it. And in fact, that was the understanding from classical physics, and it's also the understanding that's true for quantum physics. So we can find this electron if we look for it. So let's suppose that at time 0, let's say on Monday morning at noon, we look for the electron and we find it here. All right, so there's our electron. But let's suppose that we wanted to look again. How about on Tuesday at 3 p.m.? Well, then we might find it somewhere here. And if we look on Wednesday, we might find it out here. And on Thursday, we might find it here, Friday here. And it turns out that if we look for that electron, it's going to appear at a different place each time we look, or potentially the same place, but there will be a whole bunch of places, and occasionally it'll be out here. And eventually, we're going to get a cloud of possibilities every time we ask the question, where is the electron? And so that cloud is going to wind up looking very dense, close to the nucleus, and then less dense the further out you examine. All right, that picture is one of the best descriptions of the structure of an atom, that all the electrons are somewhere around the nucleus. But in fact, until you look, you don't know where. Not only do you not know, but the best description we have is that it doesn't exist anywhere at any particular time until you look. But we'll get into that a little bit more in this chapter. All right, so that map and that shape is called an orbital. It's the three-dimensional space around the nucleus of all the places we're likely to find a particular electron with a particular energy. So let's write that down so that we don't forget it. So an orbital is the three-dimensional space around the nucleus of all the places we're likely to find the atom. I'm sorry, likely to find the electron. All right, very good. So that's the orbital. Now, what I've drawn here is the orbital for a hydrogen atom, which is spherical. And it has its highest density close, and then I guess the density falls off with a greater radius. And so if you're very far away from the hydrogen atom, you are very unlikely to be able to ever measure that the electron is there. And that's, of course, why we identify correctly in classical physics that an electron is going to stick close to its nucleus if it is bound to the atom. Now, of course, there are some electrons that can be free to move about within either a solid or by itself, but that's a different story. What I want to get to say is that these can take many different shapes. But since these are three-dimensional shapes, this is actually kind of hard to draw. So let me try, but let me finish this. Many different shapes. Many different 3D shapes. All right, so let's take a new page. Let's try to draw some of these. All right, so let's suppose we have another atom with a nucleus. And in this case, this is, again, the positively charged nucleus. In this case, it might be that it's a kind of bow tie or hourglass shape for a higher energy orbital. You see what I'm drawing there? So you would be very likely to find the electron in the upper portion on the north and on the south, but not on the east and the west. And in fact, there's another orbital. There's all kinds of different shapes. Another orbital looks something like a donut, where you will find it, find the electron in a kind of ring all the way around it, but not in the north and the south side, as I've drawn it in this case. And there's many, many complex shapes. I'll show you just a few from a chart from Wikipedia. Hopefully you can see this, where electrons with different quantum numbers or atoms with different quantum numbers are shown in the vertical axis, and then with different energies or different states, different electrons with the different quantum characteristics that we'll talk about in just a second. And I hope you can see that these are all different kind of shapes, and those shapes are characterized by something we call wave functions and probability density functions. So let's talk about what that is. Let's define a wave function. So a wave function is our description, our mathematical description, which is just a function psi, and generally it's a function of x, y, and z space. So it's a function whose square is the probability density of finding the electron at the position that you're looking. All right, so this is a function whose square is, to some extent, what I'm drawing here. And this can be viewed at on an atomic level, but it can also be viewed within solids, as we will later when we talk about transistors and interfaces between different materials. All right, so these orbitals are really important because electrons exist within atoms within these orbitals. And it turns out that each orbital, so this is, I guess, point 1, and then point 2, each orbital has a different different orbitals have, let me just say, orbitals can have different energy values and characteristics depending on their shape as well. All right, so there can be different energies for each of these orbitals in general. All right, so let's go back to something that I hope you've seen before in prior classes, and that is that orbitals have quantum numbers associated with them. And you've probably seen this in some of your chemistry classes and physics, and I hope this comes back to you. If not, please do some background reading so you can recall. All right, so we have orbitals with different quantum numbers that follow certain principles. And that is that atoms, first of all, can have infinitely many orbitals. All right, they start at 1 and then they can go to infinity depending on how much energy they're holding. Also, each orbital can have at most 2 electrons. All right, so every shape, every distribution, every orbital that we think of for an atom can only hold up to 2 electrons. Now, it doesn't have to hold 2, it can hold 1, but it can hold up to 2, that's important. And thirdly, each orbital represents a specific energy level or amount of energy, you could say. Also, it represents a specific angular momentum. And then lastly, it represents a specific magnetic momentum. And these are the specific features of orbitals that really open up the whole world, not only of nanoscience and nanotechnology, but also of semiconductors and all kinds of material science, chemistry. All right, so let's talk about these things in turn. So let's begin with quantum numbers. What am I talking about with quantum numbers? Well, basically I just mean that for each electron in these orbitals, they're going to have quantized features, quantized parameters. And the first one is the one we've talked about. It has the fancy name of principal quantum number. It's the n that we've seen before, and of course this goes from 1, 2, 3, and so on. And really this determines the electron energy. And through the Max Planck equation for energy, you can see that the electron with a quantum number 1 is going to have less energy than the electron of the quantum number 2, right? All right, but you should know that also there are additional quantum numbers. There's an azimuthal quantum number, and this is usually L, and this goes from 0, 1, 2, and so on. It doesn't start at 1, it starts at 0. And this determines the electron's angular momentum. I guess I should say this determines or describes the electron's angular momentum, which we're not going to talk too much about in this course, but certainly it's a very important property of electrons, especially in electronic devices. All right, then thirdly, you should know that there's a magnetic quantum number, and it is usually labeled as M, and that goes from 0 and then plus minus 1, plus minus 2, and so on. And this determines the electron's magnetic moment. All right, and then lastly, this is one that you may have seen or heard before. There's a spin quantum number, and this often has the variable s, which is either spin of 1/2 plus or 1/2 minus. And this determines the electron's electronic spin. And usually this is also thought of as either up or down. The spin is up or spin is down. So this is a quantum number that can only take two values, up or down. All right, so the energy, the angular momentum, and the magnetic moment of an orbital are quantized, and the quantum here means that it is discrete. Right? So the takeaway here is that the energy, the momentum, the moment, and the spin, these are all properties of electrons in atoms that are discrete. All right. Now let's talk about the principal quantum number a little bit more so that we have some language, and then we'll look at some examples. All right, so very, very briefly. So this is always a positive integer, as we just said. It always determines the energy level, and there are sublevels with the same quantum number n, and they have the same energy. So let me give you an example of what I mean here. All right. Okay, so you've probably seen this before, a chart something like this. where this is energy. And then on this map here, I want to list out the potential energies, the possible energies that electrons can take, right? So there are some electrons states that can be taken down here, which in low energies, and then there are some that are taken over here, which are a little bit higher, and I'll get to what I'm drawing in the horizontal axis in just a moment. And then there are some here, and so on. And I'm going to show you in a moment a nicely formatted chart that has this. But why am I drawing them this way? Well, it turns out that there are groupings of energies into the same energy level, and that's what these would be, and they come from the different orbitals. All right, so there are orbitals that correspond to quantum numbers that relate to the magnetic or perhaps the azimuthal quantum numbers, and they are split into suborbitals, and they are S, you've probably seen them before, P, D, and F. Right? So they are what I'm splitting up here. So in this case, we have orbitals that relate to how many states are in each orbital and each suborbital. So this one is 1s, and this is 2s. This is 2p, and this is, if we keep on going, we have 3s, 3p, and then 3D. All right. Now what I want you to notice is that s orbitals have just one, where each orbital has 2 electron states in it, right? And then each p orbital has 3. And this is 3s, 3p, and this is 3d. And then each d orbital has 5 suborbitals with 2 electrons in each. All right, so what that all means is that this basically leads to 1 orbital, this leads to 3, these guys lead to 5, and this leads to 7. All right, now if we map this, then we get this nice chart that comes from your textbook, as well as you can read much more about it on Wikipedia, that we can map the energies of electrons within an atom in this kind of way and separate them out by their orbitals and suborbitals, the levels and sublevels of the atomic orbitals. And in the vertical axis, of course, this corresponds to the energy, so those that are up here have more energy than those down here. And remember that the principal quantum number 1, 2, here it is 1, 2, 3, 4, 5, 6, and so on, that relates to how much energy, and in general you can see that the larger the quantum number, the more the energy it has. Good, so I hope that's mostly review, and you've probably heard that before. I want to remind you also of something that you should have seen before, and that is the periodic table, right? So here we have this chart that's organized by different groupings, and one of the key numbers here, of course, is the atomic number. And the atomic number is not only the number of protons that are in the nucleus, but it's also the numbers of the element, the number of electrons in the element. And so when we consider an example, something like silicon, we have to take each electron and fill the lowest states first. And so I hope you remember from the past, there's this nomenclature of listing out the sublevels and then identifying how many are in each one. And so in this case, silicon has 14 electrons, and so there's 14 that we have to fill in to these orbitals. So we start with the 1s, and that's the lowest energy, and it fills those. And then that's 1, 2, and then 3, 4, and then 5, 6, 7, 8, and we keep going all the way up until 13 and 14. Now, the silicon atom, as all atoms, have potential states or possible states that are higher, but they're just not filled in this ground state example. So let's look at another example, and this one is a little more complicated. It's titanium, and in this example we have 22 electrons, and so of course we occupy in this ground state atom many more than silicon, and we get out to 22. And if we wanted to write down how those electrons are distributed with this suborbital description, then this is the way to do it, and we'll do some homework on that. All right, now I promised you that I'd show you some better views of orbitals, and this is what we drew in our notebook, of course, and this is a cloud or a 3D map of where you'll find the electron. But please do understand that for larger atoms, atoms like titanium, like silicon, like iron, like all the ones that we saw in the periodic table, the three-dimensional shape of the orbital can be actually very complex. And you should remember that in the center of these is the nucleus, and of course, for atoms with lots of electrons, then these are all superimposed on each other for a given atom.